Energy. So we've been talking about energy through the Earth's climate system and things like that. We haven't really gotten into the nuts and bolts of energy in kind of a mathematical perspective. So energy is the ability of something to do work. In the realm of physics, work has a definition, right? It's you can take a mass and you move it a distance, right? That's work. So this isn't a physics class. We're not going to, go through some of the derivations of that stuff, but I did want to talk about some basic definitions because these are the things that are going to come up when we're discussing energy balance, right? We need a terminology or a way to talk about energy. I want to mention this guy, James Joule. He was a British guy. His family owned a brewery there, the Joule Brewery, something like that. And he was really interested in kind of the onset of physics, right, kind of around the Industrial Revolution. What he wanted to know is in order to make beer, you have to boil water. All right, you add barley sugar to it, you add hops to it, and you boil it for a certain amount of time. An hour or something like that. And at the time, there were lots of different options for heating, right? You could use wood, you could use electricity. There's lots of modern ways we could think about the same thing. But what James Joule really wanted to do is he wanted to know, well, how much energy does it take to boil water? And so he began quantifying volumes of energy doing this thermal work. Skipping a lot of the kind of historical details, the modern kind of fundamental unit of energy is actually what we call the joule. So a joule, this is our fundamental unit of energy. It's actually it's a Newton meter. A Newton is mass times gravity, and then you move it a meter, like I said. But that can be applied to lots of different types of energy. A joule, at least for our purposes, we're going to think of as a unit of energy. 1 joule is 1 unit of energy, one ability to do work. Along comes this other guy, and he starts thinking about energy, but over time. And actually, the unit that we recognize from James Watt is the watt, right? Which actually is something you're probably more familiar with than the joule. And a watt equals 1 joule per second. So a 60-watt light bulb, like an old incandescent style, not an LED. So a 60-watt light bulb consumes 60 joules every second, right? So we call it 60 watts. 100-watt light bulb, 100 joules per second. So what does this all mean for climate science? Well, we need to talk about energy, and the energy that we have, the energy forcing on Earth, the primary one is actually the sun. So I want to talk about how energy comes from the sun to Earth, and then we'll talk about the energy balance a little bit. So here I drew a picture of the sun. It's a circle. The sun radiates energy out in a spherical pattern, right? The sun's rays travel kind of out in this kind of ever-growing sphere, if you were to think about it like that, from the sun. That energy has to do with nuclear fusion of hydrogen atoms, among others, loss of mass. We start getting into E equals mc squared, right? I actually love to get into that, but I'm not going to. So energy from the sun travels through space, right? And so when energy is traveling through a vacuum, that's kind of radiative energy transmission, right? So it's traveling through space and it hits Earth. Now, actually, we're going to rehash some of the concepts that we met in week 1, although hopefully with a little bit more understanding. So if we're over here, we're the little Earth getting hit from this radiative energy from the sun. Well, we know how much energy we're getting hit by. And actually what we call the solar constant is we're getting hit with So the solar constant, the amount of energy that we're getting hit with, is 1,360 watts, joules per second, per square meter. Now, that's something that we kind of will have to pick apart here. So let's say we've got the Earth. It's a sphere. Actually, it's a shape called a geoid. But and then behind the Earth, I'm going to say there's a wall or a piece of paper or something like that. And we're going to shine some light on Earth. Well, these lines that I drew here, this energy is coming in at 1,360 watts per square meter. And if we looked at our piece of paper here, it's going to cast a shadow. So the Earth would cast a shadow on this piece of paper, and the rest of this piece of paper would be getting hit with this amount of energy, but half of the Earth is getting hit with that much energy. And again, the problem is that it's going to be a curved surface. So the solar constant doesn't affect Earth the same way in every location. Okay, so I've drawn these lines of radiation coming from the sun, and remember, we know how much that is, really precisely. But if we were in, if we think about the Earth here at the equator, the surface of the Earth is roughly parallel to the incoming solar radiation. So in that case, we would receive a maximum amount of solar radiation. What we're going to see is that that's actually not this number because there's albedo. But we're gonna kind of circle back to that. So we're not there yet. Let's say mid-latitudes, we might get less energy, and then in the polar areas, even less energy, right? And so this number, or thinking about the energy that we get from the sun in terms of watts per square meter, well, that's not evenly distributed, right? That's mostly focused here in the equator and depleted in the polar areas. So again, I drew Earth. This time we actually are going to talk about albedo, and we're also going to talk about how that energy is not evenly distributed. So we have an atmosphere. Some portions of that atmosphere are clouds, particularly high clouds like cirrus style, kind of high wispy clouds in the kind of upper portions of the atmosphere, 10 or 15 kilometers up there. Some areas of the Earth are covered with ice. There's lots of different things that affect the reflectivity of Earth. So when this energy is coming from the sun, remember it's largely in the form of shortwave radiation. So at least in the context of greenhouse gases, it can punch through the Earth or through the atmosphere pretty well. But some of that gets reflected. The other thing to think about is, remember, we've got maximum input of heat here because we're basically parallel, and minimum input of heat here in the poles. So, I'm going to kind of skip you the gory details. There's actually lots of equations we can work through to do this. But what we know is that if we look at this amount of energy coming from the sun, lots of that energy getting bounced directly back into space, still in the form of shortwave radiation, the fact that we've got lots of square meters here getting lots of energy, lots of square meters here not getting very much energy. So if we think about an average square meter, right? Some are less, some are more. Albedo kind of changes all over the world. One number that we could get just to kind of allow us to start talking about the Earth system, at least in the context of watts per meter squared, is 238 watts per meter squared. That's a lot less than our number that's coming from the sun here. But remember, a lot of it is reflected, and then a lot of it, the maximum is only absorbed in the equatorial areas. that absorption really drops off as you go both to the kind of north and south polar regions. So about 240 watts per meter squared. It's a good place for us to kind of start this conversation.